All right. So 405. Yeah, I don't know. Mics aren't great. I'll try and raise my voice a little bit. Let me know if you can't hear anything. Um, Today is February 5th. So this weekend you have tutorial. Apparently a couple of mistakes. I'm not sure how they got there. Oh, yeah, before I do my thing, there's an announcement. Uh, Sorry? It doesn't seem to be working well. I don't know. If you want to, you can try it.
Hello,
Oh,
everyone.
yeah.
Today I'm just talking about the future elections that are currently going on. So as some of you may know, yesterday you would have received an email in your accountant's email titled CUSA General Elections. Essentially, this is your chance to be able to pick who you want to be to represent you to the university for the Students' Union. In the ballot is going to be the list of candidates for the presidential election, as well as the different faculty members from whatever faculty you're in. So if you recognize anybody from your faculty, then you can as well vote them in. If you don't, you can also just press submit vote. So this year, I'm currently one of the candidates that's running for president. My name is Sean. I would really appreciate your support. So when you can, make sure you take time to vote. The voting closes tomorrow at 5 p.m. So I just want to tell you guys that I think it's an important choice for you guys to make, because the student union makes decisions like, the student fees, the food options on campus. They're the ones that we're the ones that advocate to the university on your behalf as well. So when you have the time, please take the time out to vote. Thank you so much.
Great. Thanks. Good luck, man. Okay. So yeah, tutorial 4, there were a couple of mistakes somehow. I don't know. Anyway, these are there are sort of a class of mistakes that are like common sense fixes, right? So one of them is that I don't have using namespace standard at the top because it was included through another file. So just put that at the top of the test file. I have released an updated version, but if you can just fix your own. And then the other one was there was 2 instances of a variable called red. So just rename one to red2 or something. Should be an easy fix. Okay. Tutorial 5 is out. It's a little bit different in that, well, the tutorial itself is quite straightforward. We have a collection class and it's going to do a bunch of tests on it. But the trick is you're going to submit through GitHub. Because some of you have expressed interest in learning a little bit about Git, and so here's a good opportunity for you to do it. So you're going to make like a Git account, initiate a Git repository, and then commit a bunch of stuff, and then use that to submit to Gradescope. So Gradescope will only accept for tutorial 5, not tutorial 4, will only accept submissions through GitHub. Okay. So yeah, in terms of, I know this is a busy week in general, so I'm not really like super concerned about the deadline being precisely, right? It's Friday and then it's a 24-hour grace period, or maybe I think it's a 32-hour grace period actually. If you need more time because of midterms, just let me know. So yeah, that's where we stand right now. Any questions? Okay, so today we're going to, yeah, incidentally, neither here nor there, but so I am, in some sense, part of a computational geometry group, like not really, because they're research professors and I am a teaching stream, but they let me hang out with them. So, but they are this week in Barbados. Because it's a little known fact, you can't do proper math unless you're on a beach in the Caribbean. So, so good for them. I'm a little bit jealous of being stuck here in this freezing cold weather. But so that's just to say, if you ever get a chance to be a research professor, it's the best job in the world, right? You get, I mean, they do like research, actual research, but they take advantage of the fact that they can do it on a beach. So all right, so today we're going to talk about, well, we're going to documentation. And So the software engineering part of software engineering, which for whatever reason, software engineering means, it is almost like it means how do we handle all of these people, right? It's almost a social science rather than a science because, well, we just talk about how we need to make code modular, but what often seems to happen, and every time I do a little more research into this, I get increasingly interested. But what seems to happen is that we put up these interfaces, we make our code modular, and that is to handle the problem of having so many people working on an application. It's not necessarily about the best design, always. Sometimes it is. But it definitely does help coordinate a large team, which I don't know, I think is pretty cool, but also quite like the nice hard science of C++ programming. So today we're going to continue talking about documentation. We'll finish up UML, and then we'll get back to regular scheduled program of C++. So we left off talking about UML, and I don't think we have to go too in depth, but just a short review. We have classes that we represent using these rectangles, and there's three basic parts to them. There's the class name, and then in the next section, there are the attributes, the member variables, and then in the next section are the functions. And there's some weird syntax that we got to use. The naming conventions are sort of backwards on these parameters and variables and things like that. And also we have these weird in and out modifiers. They do give you some hints though, right? So when you're reading the UML for assignment 2, so an in parameter is, it's going to be, I'm not going to have to modify it inside the function, which means that if it's a primitive, I can pass it by value. If it's an object, I'm going to pass it by constant reference. So we're going to take const today. If it's an output parameter, then I had better be passing by reference or by pointer, right? So there are some hints there. And if it's an in-out parameter, well, that means I'm sending in something, but I also want to change the value of that thing. So that also should be passed by reference or pointer. Composition, so these are when a class contains another class. So a hockey game might contain two hockey teams. Contain being, loosely speaking, it could have a pointer to a hockey team or two pointers. And in this case, this is a bidirectional relationship, right? So my hockey game contains two hockey teams, and my hockey team contains some number of hockey games. We're not going to see many of those relationships in this class because they are a bit of a pain to do when you are, they're not too bad for two things that are aware of each other, but if sometimes you get three things that are all sort of circularly dependent, and that gets to be kind of a pain. So I think we might do this relationship, but we probably will stop at two things. So there's direction, and then there's, if the relationship is one way, hockey league contains a schedule, but a schedule does not contain a hockey league, then we use an arrow. And whichever relationship it is, we always include multiplicity, right? So here, a hockey league contains one hockey schedule, and a hockey schedule might contain at least one hockey game, up to many. All right, some of the conventions, I used to carry a big stick on this, I don't really anymore, but typically we don't explicitly show collection classes. That's not really what we're trying to design when we're using UML. Sometimes we are, right? So if we're making a library of collection classes, then probably we would want to use them. So there's always exceptions to this rule, but generally speaking, let's say I have two classes, libraries and books, and of course, books will be, library will, and maybe I have a book array class that I use. You don't really need to show that in your UML, because maybe I change it to vector at some point, or I change it to a linked list. The point is that this is not, the specifics of the collection class are usually not super important. Okay, so you don't have to show them. If you show them, it's probably this, I think this year, this semester, it's fine. If you throw them in there, great. If not, you will not lose marks. Typically, though, you don't need them. And that brings us to inheritance. So we have not taken inheritance yet. That's coming up, but you guys have almost certainly heard of it in 1406. So inheritance is where we have an is-a relationship between classes. So in this case, we have a player who is a person, right? So player inherits from person. And some of the terms that we use, well, person is the superclass of player, or, it is the parent of player, or if it's, maybe there's another thing up here that we inherit from, that would be the grandparent of player or ancestor. And, or in C++, we often refer to this as the base class. And then the subclass or specialized version. So here, player is a subclass of person, or we say in C++, derived class. I don't really care about the terms. If you say subclass, I know what you mean. This is usually like sort of C++ specific. Every language kind of has a preference as to what they use, but I don't think it's super important that there's no difference in meaning, right? So subclass, derived class, child class, those are all good. When we represent inheritance, the triangle, the empty triangle points to the parent. All right, so in this case, a NHL employee is a parent of hockey player, which means a hockey player is an NHL employee, and a coach is an NHL employee. And here we have, we have more things. We have a defenseman is a hockey player who is a NHL employee, etc. Now, when we do inheritance, for this semester at least, I'm not going to be super picky about what you put in the player class that you inherit from the person class in this instance, right? So because this is, because player is a subclass or derived class of person, it inherits these attributes, but you don't have to put them in the player class, right? I can look at this diagram and see that. It also inherits these functions. You don't have to put those in the player class either. I think it's a good idea if you're overloading or overriding a function that you should include it, right? Because it's a UML diagram. We're trying to communicate stuff. We're not trying to just like exactly match the specification. I want you to read this and understand something. But I'm not going to enforce that. You can do sort of whatever you want in terms of whether or not you should include these in your derived class. It's up to you. Do's and don'ts in general do not show constructor, destructor, right? We know they exist, but there might be different versions. And really that's an implementation decision. At this level, we're sort of above all that, right? In some sense. Getters and setters, we don't really encourage making unnecessary getters and setters in C++, but I don't necessarily discourage it either. If it solves a problem, then you should definitely use them. But we don't, right? We just kind of, that's again an implementation time decision. And of course, we don't show collection classes. Also, I may have even broken this rule in the assignment. Because this is sort of like it's on, I want to say spectrum, but that's not really the right word. It's on a sliding scale. It's not really black and white here because a string is technically an object, but we treat it as a primitive. And so in this sense, well, if this object is important enough, represent it with its own box, right? If this class has its own box, then what I should not do is this, right? So I have a student and I list it among the member variables. That's technically correct, but it is better to do it this way because I have an address box, right? So I think I'm not sure, I can't remember, for rectangle, maybe I bother to put one of these. I don't remember, but rectangle was really like rather than pass around 4 ints all the time, we'll just pass around this rectangle struct, right? Like that's just, I mean, that is a decision that X11 did make, but it's called an X rectangle and it uses a short int, which means that we get a bunch of compiler warnings if you try and use them because we used ints instead for no particular reason other than oversight, I suppose. So I just made this rectangle struct to like make passing around these values easier. But yeah, so just try and remember if a class is important enough to have its own box, then you should put its relationship, you express composition this way and not this way. All right, so that's it. That's the UML specification. So probably for assignment 3, you will be building a UML diagram of the resulting application. It's not, I have sort of a prototype that I probably might change, but I think mostly it's at a point where I'm kind of satisfied with it, and it's a lot of inheritance there. So your UML is going to be, quite detailed. So when you make it, so I recommend, or at least, this is a good piece of software, draw.io. You can download it on the Windows Store or the Ubuntu Software Center, Mac, I don't know, maybe, I haven't tried. Probably it's there somewhere. But at the very least, you can open it in a browser. It works just the same. So you can use it anywhere. And that's what I use to draw these. If you want to use something else like Visio, go ahead. I'm going to have to ask you not to hand draw them, okay? Because, well, what happens is there's a lot of you who will hand draw them and make very nice diagrams, and there'll be no problem whatsoever reading them. And then there'll be a bunch of people who at the last minute scribble something on a piece of paper and then cross some stuff out and then draw some arrows and then take a picture in the dark and then upload that and expect like the TAs to parse all that. And so that's what I'm trying to avoid. So like my apologies to those of you who would have taken the time to do it neatly, but just please use a piece of software to make everybody's life easier. So yeah, that's the questions. Okay, so WooClap. Well, we haven't been there for a while, and I had one and I just forgot to do it. So let's do a short review of dynamic memory. So yeah, let's give you guys some time. Again, just a reminder. So I did notice, so I'm going to try and compile like participation marks, right? Just some bonus stuff. I did download an Excel file, and I noticed that some of you have, some people, not in this class, maybe in this class, have signed in anonymously somehow. So you have, instead of your name, it says user number or whatever. So that's no good for me, right? I don't know who you are. If you don't, so if you have some, I don't know what you actually see as a student, but if you have an option to sign in anonymously or not, and you want those marks, then do not assign in anonymously. Use your school account, please. Well, yeah. See what we remember about dynamic memory and pointers. So here are two variables, an int I and an int pointer, I pointer. And now I want to point I pointer at the variable I. So which one of these is correct? Right. So this way I have my variable I and then I pointer also points to I. Yeah. All right. Well, I am not fooling anyone today. Oh, yeah, spoke too soon. Yeah, so I am going to leave it up, right? So if you want those participation marks, I'm not going to close it right away. I'll close it like at the end of class. So that anybody who like tunes in can submit an answer. But yeah, the answer is 4. I pointer is a pointer. That means it stores a memory address. And the ampersand is the address of operator. So I take the memory address of my integer I, and that can be stored in a pointer to an integer. So yeah, number 4 is correct. So I pointer is now pointing to the variable I, and I want to set I equals 50 using the I pointer, not using I. So what's the correct syntax for that? Yeah. And just remember, there's no points for right or wrong. This is just participation. All right. Well, seem to cluster around number 3, and that is correct, right? So I take a pointer, I use the dereference operator, and essentially after that operation, I have an int or whatever I'm pointing to, right? So whatever the type I'm pointing to, if I dereference, I get back that thing, which in this case is I. So this, dereference I pointer is the same as saying I equals 50, or yeah. So number 3 is correct. This is, okay, so this one's a little tougher. I have a pointer, and then I have a variable p, and I say set p equal to the address of my pointer. And so what is p's type? So maybe next time I won't show the answers right away. Maybe you can see them, I don't know. But yeah, you sure get a big hint right off the bat, huh? So yeah, if we look back at this, P gets the address of a single pointer, and when I say address of pointer to, those are synonymous, right? Those are the same thing. So the address of a variable is the same as a pointer to that variable. So yeah, double pointer gives me the address of a single pointer. Okay, so considering the following array declaration, where in memory do we expect these features? Right, so I have an array and I have students. Where are they? I'm going to wait here for a second to see some votes. This is incidentally sort of related to your tutorial 4, where you have a bunch of arrays and you're playing with, I guess, well, return types and stuff, but that's, a return type is the same as what would I use? What kind of variable could I store this thing in? Oh, fooling nobody. Yeah, so, right, I have my main. It's a stack frame. I statically allocate an array of students. So I have an array of 10, and inside each of those 10 locations is a student object with the default constructor called on them. So yeah, that's, oh yeah. So what about for this one? Where is all my stuff? And I think if I was thinking, I would have given you more options to choose from, such as, well, no objects are created. So there's some hints in the answers there, but Okay, so one of the hints is, of course, we do have a new operator. And what does the new operator do? Well, it definitely puts something on the heap. So the question is, what did it put on the heap? And, oops, did I do the wrong thing? I did the wrong thing. Array on the heap, student objects on the heap. So yeah, it's everything is on the heap in this case. So what we did is we said we have a student pointer that is on the stack, and we said new student array that goes on the heap, and in each of these is a student object that has its default constructor called on it. So yeah, in this case, both students and array on the heap. Do we have something else here? Oh, so we have, we declare a double pointer to students. So now how do we make an array of student pointers on the heap? And this is the sort of thing that it's, well, obviously you got a big hint here because number 4 is often the lead, but some of these syntax things, it's okay to look them up, right? Like arrays and a heap and stack and objects and pointers, it can be, if you work with C++ for a while, it'll be second nature, but when you're learning C++, it can be really hard to keep straight. So I would definitely, but yeah, if I'm putting, what did it ask for exactly? An array of student pointers on the heap. Yeah, that's number 4. So number 3 would, you would get, that would not compile, but you would, new student 10 would put an array of student objects. Number 2, would that compile? I don't know. I'm not sure actually. You'd probably get a compiler warning because that would be a temporary variable on the stack. Number 1 probably wouldn't compile. Is that it? Yeah. All right. So great. So a little bit of woo clap. Any questions on any of the memory management stuff? Okay. So we're going to talk about encapsulation. So we have talked about encapsulation with reference to making code modular, right? So encapsulation is the idea of hiding implementation details or making them private, or in other ways, making sure that only the things that I want to have manipulated are manipulated. So we're going to talk about that, but we're also going to talk about, because it's C++, of course, there's ways to break all of those rules. So we're going to talk about that as well. So composition, constant, relationship, and static class members. So composition, so I said composition, or maybe, I don't know, maybe I didn't say it, but composition is where one object contains another. And so there's basically sort of 2 ways to think about it. It can contain like a pointer to an object. And then it's not contained directly with my memory, but it points to another object, right? So in sense of a UML diagram, whether it is statically allocated or dynamically allocated, does not matter, right? It's still composition. For this example, though, we were interested in statically allocated, right? So in this case, I have a student class, and in my student class, I have an address class. And this is kind of how it would be laid out in memory, right? So I would have these are my student member variables, and address is also a student member variable statically allocated. And so all of the address member variables are stored alongside the student member variables, right? So given that this is how our student is lined up, well, we'll come back to this. Let's just jump right into the code. So I have a student class, and in my constructor, I take in some student information, but I also take in some address information, right? So I want to make my student, of course, the student has an address, but like really an address is not super important, right? It's sort of, I don't really want to deal with directly. I don't care about making like an address library just for my students. So I can just use another address library. It's sort of peripheral to the things that I care about, but it is something I care about, right? I want to have it on file. So the idea is that instead of like writing a bunch of address code inside my student class, I'm going to use this a pre-built address object or class. So now in my address class, well, it's just another entity object, right? So it's just a low level, contains some information. And it has like a print, which I guess we'll use. And it has a constructor, it has all default arguments. So I want to store an address. I'm going to statically allocate an address inside my student. Great. Okay, so now in my student constructor, everything's been initialized except for my address, but I'm going to leave that for now. So we've put an address in our student. We've declared when the student is made, and also we declared when the address is made, and when the address is destroyed, and when the student is destroyed. Copy constructor and destroyed. Okay, so now we have a little piece of code here. We're going to make a student stu and print stu out and see where that leaves us. 10 A. Okay. All right, so it's a little crowded here. I should have put some formatting, but here's where the student was printed. If we look at the print, it prints everything and it doesn't print the address yet. We're going to conquer these as we go. But let's take a look at the constructors. So my student constructor was called, but the address constructor was called first, right? I didn't actually explicitly call it, but the same as when we statically allocate an array and then of objects, then every object in there has the default constructor called on it. Well, it's the same thing in terms when I statically allocate an object inside of another object. When I make that student object, the address object is automatically made for me. Okay, so in this case, it called the default constructor, and it called it before the student. Okay, this is sort of important. We'll motivate it a little bit later. When we're destroying the student, right? So when the student falls out of scope, it gets destroyed. The destructor for the student is called first, and then the address destructor is called second, right? And so why this one? Well, I mean, in this case, it's just a simple address, and it wouldn't really matter if we, what order we did it in, but let's say this was a file that we had to use. Then it makes sense that I make the file first, and then in the student constructor, I can use that, right? So I construct all the resources first, and then I construct the thing that contains them. And then on the way out, well, I want to close the file, and I can't do that if I destroy it first. So I'm going to call the student destructor first, and then close the file, and then destroy the file. Okay, questions? All right, so this order, this incidentally was, I asked this on the test one, and then afterwards I realized like, oh, I didn't actually teach you guys this, right? So everybody got the mark for that. I may have mentioned this earlier. So yes, you all have at least 1 out of 17 at this point. But yeah, so my bad. Okay, so a couple things we have. So our student printed out, but our address did not print out with the student. So let's solve that problem first. Well, one thing I might consider doing is, of course, maybe I want to control how these things are printed out. So I might try and print out the student or the address. Of course, the address is encapsulated, right? These members are private. I don't have access to them. So in order to not violate encapsulation, what I would do is, well, I mean the address class knows how to print itself, so I would just do home address dot print, right? So this idea of my home address class. My address class has an API. It has some publicly available functions that I could use, and one of them is print, and so that's how I'm going to use it. Okay, so yeah, this maintains the encapsulation of home address. Let me just add a little bit of formatting. Okay, so now my student, this is student stu, their home address is, well, we have default values there. So the address got made, but it called the default constructor. Okay. Let's go and initialize that address member. All right, so for assignment 1, how we did it? Well, it was slightly different, right? Because we had an array of objects, but we did something along the lines of this. Home address equals address, number, street, city, province. Right? For assignment 1, this was, we assigned it into an array. Like when we added something to the panel, we would assign it to the array using this sort of format. And this will work. This takes advantage of the assignment operator. So let's, don't take my word for it. If we write out the home address now, we have the correct address. That's great. But when we look at how it was constructed, so the address constructor was called, then it was called again, and then the destructor was called for the address class, and then the student constructor was called, well, sort of. Let's move this up here just for fun. So yeah, address constructor, and then so my address is made, and then I start making my student, and then in my student I make this temporary address, which is this call, and then as I exit the student constructor, I destroy that temporary address, and this is wasteful. I'm making an extra address just so I can copy in these values into my address that is contained inside of my student class. So although it works, we're making a lot of extra copies that we don't need. So what we really want to do, address, the constructor is called first, so we want to, before even the student constructor runs, we want to be able to pass arguments to the address class. And so we're going to use a new syntax. It's a member initializer syntax. So if I look at the implementation of the student constructor in the parameter list, before I enter the block, I put a colon and home address, and then I can put number, street, city, province. Okay, so let's divide it across a few lines. So this grabs my home address class before the constructor is called and says, here, take these arguments, right? I'm using arguments from the parameter list, so these are scoped in. Give it to the home address class, and when you call the constructor, supply those arguments. So if we run this again, I should have only one call to the address constructor here, and then one call to the destructor down here, but this is when the student is being destroyed. Okay, so member initializer syntax, it grabs the object before I can, before the constructor is called. Right. Questions? Okay, so let's, all right, well, let's back that up a second. Let's take that out, and let's not initialize our home address, and then let's say, well, we have a default constructor for address, but let's take the default constructor away. All right, so I've taken away a default value here, which means that I can no longer make an address with the default constructor. And if I come back here, oh, we can see, ooh, no default constructor exists for the address class, right? So, all right, well, what if I did this? Home address equals address numbers. Well, that's still a problem, right? Because by the time I get here, the constructor is already, it already tried to call the constructor. It couldn't because it doesn't have a valid constructor it can call. So if I have a default constructor, then I don't need to do this. I can get the default values and then update them later. But if I don't have a default constructor, then I have to use this. Okay, so this is really the best way to initialize like really anything in C++. Yeah. Questions? Okay. It's not only the home address we can initialize this way. Wait, what's going on? Ooh, so I have another problem. When I took away the default constructor, now my copy constructor doesn't work anymore, right? So the copy constructor before, well, it was doing nothing actually. But now it's a problem. I have to, again, grab home address and stu.home address. So I'm going to grab the home address before the constructor is called and say, use the copy constructor with this home address. Okay, and then this should all work. All right, so beauty. It doesn't just work for home address, however, I can number. And if you look at C++ code, you might see this a lot, right? It looks like I just repeated myself. I have number, and inside the brackets for number, I put number. So down here, when I'm initializing my number, which is a string, I can, I have to, there's a naming collision, so I have to say, well, this number is equal to, this is my member variable, and this is the argument, right? And so this works here, but up here, when I use member initializer syntax, I don't have to do that, right? The compiler is going to look at this, and it's going to know from the context that this is the member variable and that this is the argument. And you can even see student, the scope resolution operator for student is there. So yeah, I can do, well, here, you can do everything. I can do major program. I can do GPA, which is a primitive, right? It also has a constructor. And then I don't need anything in the constructor body, right? I still have this, but I don't need that. I can just do this. And you will often see this in C++, right? So I have my constructor declaration. I use the member initializer syntax, and the body of the constructor is empty. And this will work just fine. So yeah. All right, questions? So yeah, technically this is the best way. In terms of what I expect from you guys, there are some instances where you have to use this, but otherwise I don't mind if you do things in the body. There's a fairly high chance it gets optimized by the compiler anyway, depending on what type this is, but yeah. All right, is there anything else I needed here? Okay, yeah. Member initializer syntax. All right, and by using member initializer syntax, right, we've not only saved a few CPU cycles, we've still maintained encapsulation of our address class, right? So our student print uses the address print because that's part of the public facing, it's part of the public API address class. And also, how do we initialize the address member variable as well? We use the address constructor, right? These are both the ways that we should do things. Okay. And just a reminder of what the member initializer syntax looks like. It comes between the actual argument list and the block, the execution block. And it occurs before the student constructor is called. And this is actually, so I have it listed here in a certain order, but it doesn't execute them in that order. It executes them in the order that they are listed in the class, right? So in this case, my student, regardless of how I put them here, they would be, the number would be initialized first, followed by name, followed by major, GPA, and home address would be last. Okay. Another thing to keep in mind, objects are built from the inside out. So the contained objects are constructed first, followed by container objects, and every object is initialized. The destructures happen in the reverse order, right? So the container object is destroyed first, and then the contained objects are destroyed. All right, so that was, that was composition, but composition using statically allocated address. Maybe we have, instead of a statically allocated address, we have an address pointer in our student class, and then we make a new address, and that goes on the heap, and then our class looks something like this. Okay, so this is specifically a problem when we go to copy the student, right? So in terms of initialization, this is quite simple. I have a pointer, I just say, well, address equals new address, and I can do that anywhere. I can use that member initializer syntax or not. But when I go to copy the student now, well, if we haven't made a copy constructor, we're going to get the default copy constructor, and the default copy constructor does a shallow copy, which means that the default copy constructor information contained here, and it copies it directly, which means my address pointer gets the memory address copied over, and it's the same memory address. I really should memory address and address, but hopefully you can follow. It's the same memory address as this address object. So now I have a copy of my student where the copy points to the same address. Now, is this a problem? That depends. Certainly it can be if I go to try and delete this in both of my classes. That's definitely going to be a problem. I can always just leave it as a memory leak, I suppose. But really what we want is a deep copy, right? So when I make a copy of this student, I do want to copy everything over, but when it comes to this address pointer, I don't want to copy that. I want to follow the pointer, make a new address, and then assign that pointer to that address. Okay, so let's take a look at that. So same scenario, we have an address class, we have some, with set cities, we're going to use these things. Address constructor, I'll leave that out for now. If we need it, we can put it back in. So my student class, I have a statically allocated home address, but let's just turn that into a pointer and then dynamically allocate it. Okay, so we're gonna have to change a few things. One is this home address. Of course, I can no longer do this because home address is a pointer and this is not what pointers take. I can still use member initializer syntax here. So you don't have to. You can do it the old-fashioned way. You can say home address equals new address, and then just pass in number, street, city, province. That's fine. I'm okay if you do that. But you can use member initializer syntax for everything, including this. How I would do it is new address, number, street, city, province, right? So new address returns a pointer to an address, and this takes a pointer to an address. So this, again, constructs a new address and assigns it to this pointer in one step, and it saves a CPU cycle along the way. Okay, we'll have to change a few other things. This move to function and the print. These are now pointers, so they take arrows. Otherwise, I'm going to make a student Stu here, and I'm going to print them out. Whoops. So there we go. Student Stu and lives at 123 Main Street, Ottawa. Okay. Of course, I have not deleted Stu, so this is technically, we have a memory leak, so let's delete Stu. But what else, right? So our little rule of thumb, I have in my constructor, I've made a new home address. My destructor, I did not call delete, right? So I should have a matching delete call for that to make sure that all the dynamically allocated memory is cleaned up when we're done, right? So now the student is sort of self-contained. Make and yeah, bad formatting, but there is the student, and there is the no memory leaks sign. So we've cleaned up after ourselves. That's great. Let's make a second student called Joe. All right. So we're going to make a student called Joe. Let's make this explicit, even though both would call the copy constructor. So this is going to call the copy constructor, pass in student as an argument. I'm going to take Joe, I'm going to change Joe's name to Joe, just so we can tell them apart. And then we're going to print both Joe and Stu. And we get something bad happens. And that bad thing is I deleted Stu, and then I tried to use them. Okay, so printing Joe and Stu. Joe is, well, same student number, same GPA, same address, but named Joe, and Stu, same thing. All right, so I made a copy. Okay, so let's try now. We're going to have Joe move to Montreal, and then we're going to print out Stu and Joe again. All right, so move to, if you don't recall, takes the home address and sets the city to Montreal, right? So that's why we introduced those setters. Okay, so sending Joe to a new city. Joe is in Montreal, and also Stu is in Montreal. Joe got deleted, Stu did not yet. But when we made a change to this address class, of course, it was reflected in both objects, both students, Joe and Stu, because they are pointing at the same address currently. Also, right, if I want it to be, clean up all my memory, so Joe gets deleted automatically because Joe is statically allocated, but Stu I have to delete explicitly, so let's do that. And then try and run it, and of course I get a seg fault at the end. So they're both trying to delete the address, the same address. After Stu deletes it, then Joe tries to delete it, and we get this seg fault. Okay, so we want to do a deep copy. Let's do a deep copy. It's not that complicated here. You will, on your assignment 2, do a more complicated version of it, which we'll talk about in a second. But here is my copy constructor. And here I'm making a copy of the home address. But home address is a pointer, and I'm passing in stu.homeaddress as a pointer. So I'm initializing with a pointer. Let's do this the old-fashioned way. Say home address is new address. And I'm going to call the default copy constructor of the address, and I'm going to pass in the Stu address. So stu.homeaddress. And of course, that is a pointer, and I'm going to dereference it. Right? So home address has a constructor. We didn't write one, but it has a default one that works just fine because it has no dynamic memory. And here yeah, so that's all there is to it. If I ask you for a deep copy, you should have new in here somewhere, right? So I have new in the regular constructor, and I should have new in the copy constructor as well. And then if I do that, should clear up some of my issues. So now we can see that when Joe moves to Montreal, Stu stays in Ottawa, which is great. These two students, no seg faults because they're deleting their own copies. And if I run it with Valgrind, where are you? There we go. Yeah, all the memory is no complaints from Valgrind. Okay, so that is a deep copy. For your assignment, first of all, any questions? Okay, for assignment 2, I think I asked you to make a deep copy of the flow panel, which just to give you an idea of what that's going to entail, it's a little more involved than this, but the principle is the same. You have a flow panel, and it has an array for text areas. And you can statically allocate that array or dynamically allocate that array. Either is fine, but this is a TA array. And inside here is a pointer to the heap where there is another array, primitive array that is, and that is pointing to some text areas. So I want you to make a deep copy of that flow panel, right? So you're going to write a copy constructor that's going to handle all of these cases. And then, if you do it correctly, the test should come back okay, and you should run them with Valgrind, right? There's some memory tests that ask you to run with Valgrind. Or if you're on a Mac, there's that leaks. It's not that hard to use. You can just Google it. So yeah, questions? Okay. All right, and that is the rule of 3 is something we talked about, and we've gotten to 2 of the parts of the rule of 3. One is, well, if we have dynamic memory inside a class, in this case, address is dynamically allocated inside the student class, well, of course, we now have to make a destructor in order to clean up after ourselves. And we required a constructor, but then we also required a copy constructor. If we made a copy of students, that is, then we need a copy constructor because, well, otherwise we end up with some problems. Like maybe I want these things pointing to the same address, but then I do have to decide who's going to delete it, right? Because if both students delete it, that's a problem. So if you need, the rule of 3 is like if I need a destructor, I probably need a copy constructor as well. Or if I need a copy constructor, I probably need a destructor. And then the third part of that is the assignment operator, which we haven't gotten to yet. We're going to get to it when we get to operator overloading, but it essentially does the same thing as a copy constructor, right? That's the idea. It just doesn't do it when the object is made. It does it to an object that already exists, but it's going to copy everything from one object to another. So you're going to essentially use the assignment operator to do a deep copy as well. Not this assignment, you don't need to do it, but just a copy constructor. Also, I mean, we'll give an honorable mention to the rule of 5. So the rule of 3, we are concerned with. The rule of 5 concerns a couple things that we're not going to do, which are move constructors and move assignment operators. And I'll explain the idea behind them, but we're not going to use them. Essentially, it is this. I want to make a copy of the student, but I know the old student is getting destroyed, right? So I copy all of these things over, and then I set this to null, and I steal that address from that other student, right? And that other student gets destroyed, but I don't, and so that other student's getting destroyed, so they don't need that address, and it would, I would just be wasting time making a copy of it and then destroying the copy. So that's what, when we do move operations, we are stealing resources of something that's going to be destroyed anyway. But we're not doing that in this class. Although, I mean, you can if you like. I'm not going to enforce it. Okay, constants. So we've talked about composition. Now we're going to talk about const. Maybe you've seen it. It just means a constant. Const means constant, but in C++, it has a whole bunch of places where you can use it. Why do we use it? Well, protection, right? I mean, the more specific we can be about types, the more errors the compiler can catch. But also, well, we'll talk about, I guess, that next slide. But so basically, if there's no reason for an object or variable to be modified, we make it const, right? So we follow this principle of least privilege. Yeah, we'll see a bunch of places where it's used. So now that we're going to start using const, a whole new class of errors from your compiler. Your compiler is going to start mentioning things called L values and R values. All right, so just to give you a little bit of background, so you can, decipher these error messages. It's quite simple. When they made the language, they decided, I assume, I don't know. But an L value is something that can be on the left-hand side of an assignment operation, right? So it's a variable. I can change the value of an L value. An R value can only be the right-hand side of an operation because I can't change it. Basically, R value is a constant, okay? For some reason, they went with R value instead of constant, but that's essentially what it is. And an L value is not a constant, so I can assign it a new value, but I can also make it the right-hand side of an assignment operator, right? So I can have L value equals L value, but I can't have R value equals R value. So example of an R value is if I have two variables, A and B, and I say A plus B returns a value, that's an R value, right? So I cannot assign 5 to A plus B. That doesn't make any sense. So this would give you a compile error. When you return by value, that thing is an R value, right? You cannot change it. This is const. You can copy it into a new object, but technically, I could not, for instance, call getStudent dot, as you're going to see. Well, depending on how this, but I couldn't call a non-const function on this. So in certain circumstances, this would be okay, but others, it wouldn't. All right, so let's make some consts. Okay, so I have a number, I have a name. These are primitives. I mean, string is an object, but let's pretend. Goodness gracious. Oh yes, I have some residual errors. Sorry, 1 second as I clean these. No spoilers. Okay, may try that again. Okay. P3, so my int is 5 and my string was, well, I guess I didn't give it a value, but let's give it good old Bob. Okay. So int is 5, the string is Bob. Great, let's make them constants. So I just use the const keyword in front of the variable declaration. No warnings from the compiler just yet. So it still works exactly the same. I can read a constant, right? So constants are definitely, I can read them. Let's try and reassign the value for number, and expression must be a modifiable L value, right? So it is a const, so it is an R value, and it cannot be on the left-hand side of an assignment operator. So this, not allowed. But also, let's say that, I didn't want to initialize it right away. This is also not allowed, right? If I make this const, then as soon as I make it, can never change it again. So I have to give it a value right away. And in the case of an int, it requires it, right? In the case of a string, not so much. Because a string has a default constructor, it's going to initialize it to an empty string. So if I don't give it a value, it'll give it a value. I'll never be able to change it now. This is just an empty string that I can never, ever change. So it's kind of useless, but it will allow you to do that. Okay, so those are primitives. The string's an object, but let's take a look at an object. So I'm going to make a date, D1, 2024. Let's do it current 2 and 5. Okay, so today's date. There's something a little special about this date object. For now, I'm going to make these member variables public. Okay, so I can access them directly from the date class. So d1.day, today is the P3, today is the 5th day of the month. Okay, and so date D1 is a constant, but I can read the member variables and print them out. Of course, when I try and do this, D1 is not modifiable. None of its member variables are modifiable L values either. Right? So the whole point of making this date object constant is that I am freezing the values of these things. Right? So these values can never be changed. All right. I didn't call any functions yet. So the date, month, day, year, these are read-only. So print is, it doesn't change them, but it says this type has qualifiers that are not compatible with the member function date print. Okay, so I can't do that. All right, so we'll come back to that in just a second. But when we're thinking about objects, we should think about the principle of least privilege. If the objects you create don't need to be modified, you should make them constant. So what does it do? Well, guarantees the integrity, sure. Helps the compiler catch errors, yeah, definitely. Allows your compiler to make optimizations, right? So it's going to make a lot faster code. The other thing is that it makes your object thread safe, right? If you can't change it, it's read-only, then I can read it from any thread, it doesn't matter. So it allows your compiler to make a whole bunch of optimizations that it wouldn't otherwise. And we are writing in C++, which means we care about speed, presumably. All right. Sometimes difficult to foresee if they should be made constant. You might bump into this in your assignments, right? So for your next assignment, you're going to make all kinds of constant functions and whatnot. But yeah. All right, let's solve this problem. So I want to print a constant object. I know the print function doesn't make any changes to any variables, but still it's giving me a hard time. So I'm going to tell the compiler, I'm going to make a compiler a promise. I'm going to say, I promise never to change any member variables in this function, right? So now this const is part, so you can see the little underline here. No function definition found for this. So this const is now part of the function definition, which means that this is, sort of different. So in order to make these two things match up, I have to put const on both of them. And now you can see I got a problem. But before we get to that, let's just get rid of that for a second. So inside my print function, I am making a promise to the compiler that I will not change any of the member variables of my date class. And indeed, I don't. I just print them out. You're fine now. All right. So today is the 15th month, and I print out, well, it's missing the month name because I had to take that thing out, but you can see the day and the year printed out just fine. Okay, so let's put that thing back in. So in my print function, I promised that I would not change day and year. But this get month name, I did not make any such promise. The compiler is worried that, yes, I did not change these things, but it doesn't have any guarantees about what happens in here. It could have been changed in there. So in my const function, I cannot call a non-const function because I have not made that same promise. So let's get month name, let's make that promise. I mean, get month name really doesn't do anything. It doesn't change any member variables, so I can definitely do this. And then my print function is fine. And there we go. So February 5th, 2025. Okay, and you'll notice I made this promise. If I try and violate that promise, the compiler won't let me, right? So this is, the compiler enforces it. Okay. So sorry. Yeah, one more thing. Any questions so far? Okay. So I said that changed the function signature when I put the const on it. And so you may have also noticed, wait. I just did it in a different place. That's fine. Okay, so let's copy this over. Let's get rid of all this. We don't need it. Let's make a non-const date, D1, 2013. That's, wow, so long ago. D1. Oh, yeah, so this is today. Okay. So I have a date D1 and then date today. D1 is not const. Date is const. I print them both, and yeah, so January 28th, 2013, and today is February 5th, 2025. So the print function works for both of these objects, right? The const version, const version. So the idea is that whenever possible, you should make your functions const, because if you do, well, first of all, if I make my object const, then I can still call that function. I can call that function on an R value, right? If it's a return variable or something else like that. And of course, it allows certain optimizations to be made. Maybe, however, I want to have a different print function for my non-const objects. I can definitely do that, right? So I'm in the wrong place, but up here, I can have a second version, right? Because this const means that this function signature is different, so I can overload it with a different function. And then here, I'm not going to actually print it. I'm just going to say that we're in the non-const version of print. Let's actually say non-const. Okay, so now I have a print with a const, and I have a print without a const, and I have a object that is const and a second object that is not const. So date in 2013 gets the non-const print. My const date gets the const print. Okay, so this, you will see actually places where this comes in handy when we get to operator overloading. Yeah, questions? All right, somebody asked me if you can force it to call the const version on a non-const object, and I have not been able to figure out a way how. The closest I could come is this. Oops, let's do const date. So I'm going to cast this to a const date, but you'll see that this does not actually call the const print version on the D1 object. And it actually copies that thing. It makes a copy of my D1 object into a const object and then calls the print on it. So yeah, I don't know. I have not figured out a way. Maybe like a 3-second Google search could give you the answer, but I did not. I don't know. Anyway, questions? All right. Okay, so yeah, putting const at the end of member function declaration guarantees the function will not modify any of the member variables in that object. It's pretty strict, right? So if I have, for instance, a student and an address pointer that points to an address, I say const student, and the promise is that I am not changing this value. I do not say anything about this value. All right, so it means I cannot point the pointer at a new address, but I can follow the pointer and make changes to the address that it's pointed to. Right, so it is very strict about that. It does not follow pointers. If I make a const object, it just looks at all the information that is directly there. It doesn't follow any pointers. And of course, there's a cascading effect to this stuff, right? So when I make a function const, or as we'll see later, when I make a parameter const, it can have this cascading effect where I have to now go change this, and now I have to go change this. And in most cases, that's a good idea. You should make as many things const as possible, but occasionally we'll get to a certain point and realize, I can't do that. I need to change this variable here, and then you have to kind of roll back all those changes. So that is one of the things you're doing for assignment 2, is applying const everywhere possible. Also for your tutorial 4, I believe I asked you to, sorry, let me think for a second. We didn't get to static members, but So if any of you have any trouble with tutorial 4, in the sense that you do not have enough information to finish it, just let me know. I don't know. We can push the date back if necessary. Although some of this stuff, it's okay to figure it out, or at least try to figure it out yourself without actually knowing all the details, right? Because then when we talk about it in class, you'll be like, oh yeah, that's why that does that, and whatever. So do try it. If anybody has trouble meeting the deadline, let me know. I'll push it back. Not a problem. I think you have most of the things you need, but yes, tutorial 4 might need static functions as well. Tutorial 5 is, you need const. It should be fine. So yeah, I think I will leave you with that for today. Yeah. So principle of least privilege. Let's just briefly talk about, so there are, I said in some cases it's hard to figure out what's going to be const, but in some cases it's pretty easy. So there are like some really easy marks you can get here. So your print functions, make them const, okay? Your getters can be const. Maybe next week we'll talk a little bit more. There's some stuff there, but for the most part, all your return variables, you should be returning by value, right? You can return by reference if you want, but just so you know what you're doing. We're not going to worry too much about return values. So getters that return by value, you can make them const. All of these simple Boolean functions like less than, where I'm just comparing things, I'm not actually changing anything, less than, equals, those can all be const as well. So those are some good easy marks for your assignment 2. All right, so that is, what is today, Wednesday? Yeah, so that's it for this week. I have my office hours tomorrow if you need any help. And, you know, if you run into trouble with the tutorials, just let me know. I'm pretty flexible about these. I can't extend them forever because then, I don't know, just a logistical nightmare, but